Here we're going to talk about logarithms and what they are and how to use them. So logarithms are basically the functions that are inverses of exponentials. What I mean is we have kind of this like formula right here for it, where we have y equals b to the power of x, and x equals log base b of y. Let's talk a little bit more about what that means. So that means is that if I'm saying like 6 to the power of something equals 36, right? Normally when we have an x value, we are trying to solve to find what that is equal to. In this case, when we look at it, we know, okay, hey, 6 to the power of 2 is equal to 36, so x is equal to 2. Logs are a little bit more mathematical way to solve these because we're going to start getting into these problems where it's not as easy. Like if we had 6 to the power of x equals 25, well, there's no easy number necessarily to figure out what x is equal to. But logs are a way for us to solve that. And the way we can do that is we're going to rearrange these problems into logarithms. And so in that, so for example, let's just take this problem right here and rearrange them into a log. Basically what happens here is the x value, what is normally the exponent, is going to be by itself on one side of the equation. So I'm going to start with x here. The base, or b here, becomes the base of the log. So we're going to say log base 6 because we get that number from the base of the exponent. And then lastly, the y value, which is what was by itself originally in this problem, which is 36, ends up being what is inside this log here. So in this one here, we say that x is equal to log base 6 of 36. So these two equations here are equivalent. 6 to the power of x equals 36, and x equals log base 6 of 36. So now we've kind of solved for x. We have x equal to all of this stuff here. And again, it still just means 6 to the power of what is equal to 36. That's kind of what log is asking. So let's talk about the domain and range of a log function. Because they are inverses, a reminder that the inverse of a graph here, we're going to say that this exponential here is the red graph. And so what we know from the last unit is that exponential, we have a domain of negative infinity to positive infinity. It goes all the way to the left and all the way to the right. And the range is always, whatever this horizontal asymptote is, that's the lowest, and then it goes up to positive infinity, unless we get into negative x values and all that kind of stuff. But for now, we're just going to talk about the basics. So inverses are always a reflection over the line y equals x. So what that means is that if you see this red graph, the exponential function, if we were to flip that over this dashed line here, y equals x, we'd land on this blue line, which is the logarithmic function. So again, for inverses, we flip that over. So if we're talking about domain and range, remember the domain of our original function, the exponential function, was all real numbers. But what you see here is that on the, let's go ahead and mark this up, on the exponential function, it never crossed that horizontal asymptote. That part of the function there is getting closer and closer and closer to 0, but never crossing it. When it flips over this y equals x, well, now that part of the line is right here, and same idea. It is not crossing this line, but it is no longer a horizontal asymptote. It is actually a vertical asymptote. So this line never crosses this line here, and then when we continue this logarithmic function, it goes on forever in that direction. So for the domain, it stops because of a vertical asymptote, whereas the range now is going to be all real numbers because it goes down to negative infinity and up to positive infinity. So if we're going to rearrange these problems, so if we look at exponential and logarithmic, what I originally had written here, another way to think about it is how to rearrange it. Something dumb that you can think about that will never leave your head is that we love logs. Logs are the best. We are so excited to be working with logs. Logs are bae. And what we mean by that is that if I have some sort of like 6 to the power of 2 equals 36, if I'm trying to change that into a logarithm, well, we take the base of this exponent, so it's going to be log base 6, because that's the base. Then the answer, which is 36, equals the exponent, which is 2. So in this here, if I were to say, hey, what is log base 6 of 36? What I'm looking for is 6 to the power of what is equal to 36? In this case, it is 2. So if we're rearranging them, log of a base is the answer equal to the exponent. Now, if we're going to go ahead and rearrange some of these here, we have 3 to the power of 2 equals 9. So I know it's going to be log base 3, because that's my base, of the answer, which is 9, equals the exponent, which is 2. For number 2 here, we have the base of 4, the answer of 64, and the exponent of 3. Base of 5, answer of 78,125, exponent of x. And hopefully you see here now why logs are helpful, because now we have x by itself here, so we can solve for it just by taking log base 5 of 78,125. We can also go in the opposite direction, right? So if we have log base 9 to the power of x equals 81. Again, this is more helpful in using things that are not calculator based, where we say 9 to the power of something is 81. Now I know x is going to be equal to 2. Same idea with this one. We have the base of x, the exponent of 5, and that is all equal to 32. So we're just rearranging these numbers here. And if we wanted to try and solve for x, we would say, okay, what to the power of 5 is 32, which ends up being 2. So again, in all these situations, we have like log base 9, log base x. Even in the previous problems that we were looking at, we had log base 6 over here. Sometimes when you look at a math problem, it may not have a number for the base. If that's the case, just like when we have like x by itself, there's really this like invisible 1. Same idea with this log is that if there is no subscript, if there is no base, we're going to assume that it is a base 10. So if we have, let's say, the log of 100, that's the same thing as saying log base 10 of 100. Those two things are the same because we have this invisible 10 as our base. So let's evaluate some of these without a calculator. Remember that rearranging them might help us in this case because we're saying the base here is 3. 3 to the power of something is equal to 9. And now I know 3 to the power of 2 is equal to 9, so that's my answer. This one here, log, and this one, again, has an invisible 10 here, so log base 10 of 10 is equal to something. And now I'm saying 10 to the power of something equals 10. And so I know this is going to be 1. And lastly, we have log base 6, so 6 to the power of something equals 36 to the power of 3. So this one is a little bit tougher, but let's just look at this in a different way. I know that 36 to the power of 3 is, let's see here, the same thing as 6 to the power of 2 to the power of 3, because 6 to the power of 2 is just 36. So really that's like saying 6 to the power of 2 times 6 to the power of 2 times 6 to the power of 2, which I know is 6 to the power of 6 because of my product rule. And remember, that's what we were originally looking for all the way back here. So log base 6, 36 to the power of 3 is equal to 6. And for this final one here, we are saying, hey, 2 to the power of something equals whatever's on the inside here, so 2 to the power of 7. So what we should notice is that, well, 2 to the power of 7 is equal to 2 to the power of 7. And this is what the whole point of this is getting to. So what the point of this is that we see that if we take log base 2 of an exponent with the base of 2, these two things are actually going to cancel each other out. and leave us with just this exponent. So let's say if I had log base 3 of 3 to the power of 8, I know that's just going to be 8 because if these bases match here, they end up canceling each other out and leave me with just 8. Because I know 3 to the power of 8 is equal to 3 to the power of 8. And again, this is going back to logs are the inverse of exponents. So imagine if we're talking about like, hey, 3x equals 30. Well, to solve for x, we divide both sides by 3 here to give me x equals 10. This division, dividing by 3, because this is multiplication, these cancel each other out, which is why we end up getting our final answer. X is by itself then. Same idea with these logs and these exponents. The whole point is to either cancel out a log or to cancel out an exponent. Let's do a last couple here. If we have log base 2 of 2, we're saying 2 to the power of something equals 2, which I know is 1. Again, these are canceling out, if you notice. 5 to the power of something equals 5. Well, I know that is also 1 because these are canceling each other out. Log base 5 of 5 to the power of 2. Well, 5 to the power of what equals 5 to the power of 2? So I know my answer here is 2 because these are canceling each other out. And that's the basics on logs.